Hi, this lesson is a pre-calculus review for Math 114. So let's start by talking about lines. So there is a couple of different ways you can express a line, but this format, which is called slope-intercept form, is very convenient because you can pick out the slope, which is the coefficient of x, and the y-intercept. So the coefficient of x is m, that's what we call the slope. That's a measurement of the inclination of the line. And the y-intercept, or the point where it intersects the y-axis, is the point 0b. And the y-coordinate is this number right here, b. We can compute the slope of a line by if you know 2 points on the line. And so the slope is computed by doing the difference in the y-coordinates divided by the difference in the x-coordinates. You can also find the equation of a line by using the point slope formula, where you plug in the point x sub 1, y sub 1, which is any point on a line, and the slope m, and solving for y, and then you will have a line in slope-intercept form. So we'll be using all of this information in calculus. Another important function to understand are your quadratic functions. The graph of a quadratic function is a parabola. A parabola can be stated in this form: ax squared plus bx plus c. And you can compute the vertex of the parabola by finding the x-coordinate by plugging into negative b over 2a, and then finding the corresponding y value of the vertex by plugging in negative b over 2a into your original function. We will learn other ways to find the vertex by using calculus, but for now, this is one way to find the vertex of a parabola. Whenever you're graphing a parabola, you want to make sure you show the vertex on the graph. Remember that the graph, the parabola will look like a U shape. It will be an upside down U when your A is negative. And in that case, your vertex would be considered a maximum point, and your parabola will be facing upward like a traditional U shape when A is positive. And in that case, your vertex would be considered a minimum point. We should also be familiar with the equation of a circle. So remember, a circle has a radius r and a center at hk, and standard form of a circle is h minus x squared plus y minus k squared is equal to r squared. So remember, when the center is the origin, you would simply have this equal to r squared. So this is with a center at 0, 0. All right, so now let's talk about radicals. Radicals and being able to manage them will be important for calculus. Radicals come up a lot. So this is considered to be the nth root of a to the x. So the little number in the corner here is the root. When you don't have a number written there and it's just written like this, that would be a square root. So n is the index or the power of the root of the radical, and a to the x is what we call the radicand. You should always leave radicals in simplest form. So if there's any perfect roots inside in the radicand, you should take that out. And you can rationalize your radicals, meaning if you have a radical in the denominator, we typically remove the radical from the denominator, but it's not quite as important in calculus as it was in our algebra and pre-calculus courses. So you'll see how we manage our radicals throughout this course. So here's an example. If I need to simplify 8x to the fourth, well, 8 is not a perfect square, but 8 can be rewritten as 4 times 2. So the square root of 4 is 2. That comes out of the radical. The square root of x to the fourth is x squared. That comes out of the radical. And the only thing that wasn't a perfect square and stayed inside the radical is this 2 right here. So that stays inside the radical. So your answer is 2x squared root 2. So similarly, this one here is a cube root. 27a cubed, the whole thing is a perfect cube because 27 can get rewritten as 3 cubed, and a cubed is a perfect cube. So the cube root of 27a cubed is just 3a. Since that's the entire thing is a perfect cube, there is no radical left in your answer. And then here's an example of how to rationalize a radical when you have a quotient with a radical in the denominator. So in this case, it's a square root. So we're going to multiply the numerator and the denominator by the square root of 3x. That gives us 6 square root 3x, and square root 3x times itself, right? That becomes a perfect square inside the radical. So that's just 3x in the denominator. But then you have to follow the rules of fractions, which is leave it always in simplest form. The 6 and the 3, 3 goes into 6 2 times, and so your final answer is 2 root 3x over x. So remember, this answer and this answer at the end are equivalent, just the one at the end has been rationalized. Being familiar with your rules for exponents will be really important as well. So here's just a reminder of some of them. So x to the m times x to the n means that you add your exponents. When you're dividing x to the m over x to the n, and then you subtract your exponents. As long as the base is not 0, you can do that. If you have an exponential expression raised to a power, that's when you multiply your two exponents. And we should absolutely be familiar with how to change an exponential expression to a radical and vice versa. And so as long as the denominator n is not equal to 1, then x to the m over n is equivalent to the nth root of x to the m. All right, so here on the right, here's an example of where we're using these first three in some way. So I have 2x cubed y, the whole thing raised to the 4th power, times 3xy to the negative 6. So remember, we leave our final answers without negative exponents. So if you have a negative exponent in the end, we have to adjust for that. So first I raised this to the 4th power, and so I got 16 x to the 12th y to the 4th. And then I have to multiply that result by the 3x y to the negative 6. So when you multiply, you get 16 times 3 is 48. X to the 12th times x is x to the 13th. Y to the 4th times y to the negative 6. Remember, you add your exponents, and so you get y to the negative 2. But then we rewrite the y to the negative 2 in the denominator, and the exponent turns positive. So you get the final answer of 48x cubed over y squared. These two examples here is how to convert a radical to an exponential expression. So the first example in green is the 5th root of x cubed. According to this rule, that's equivalent to x to the 3/5. And the second example, the cube root of ab squared. Remember, the cube root belongs to both the a and the b squared, but the squared here only belongs to the b. So we have to make sure that we distinguish that. So when you rewrite it, you get ab squared in parentheses, the whole thing raised to the 1/3 power. All right, so here's a little bit regarding right triangles. That's the Pythagorean theorem, which I'm sure you're familiar with. So what the theorem says is that if you have a right triangle, meaning one of the angles here is 90 degrees, one leg squared plus the other leg squared will equal the hypotenuse squared. The hypotenuse is the side opposite of the 90 degrees. It's the longest side of the triangle. I called it C. So that's what the theorem states, and that's used often in mathematics. And then there are identities regarding the Pythagorean theorem and the trig functions. These are called the Pythagorean identities. And the first one is that sine squared of theta plus cosine squared of theta is equal to 1. The second one is tangent squared of theta plus 1 equals secant squared, and 1 plus cotangent squared of theta equals cosecant squared of theta. So these three identities will be really important for you to have memorized and be really familiar with, because sometimes we use them to make substitutions. So here's more reminders about trigonometry. So a trigonometric function, there's 6 of them, all stated within this block here. They are basically a ratio of 2 sides of a right triangle. So if my triangle is labeled A, B, and C, as it is here, and my angle is in the lower left-hand corner, sine is opposite over hypotenuse. So opposite of theta is A, hypotenuse is C. So here's a reminder, sine is opposite over hypotenuse. So that's why sine of theta is A over C. Cosine is adjacent over hypotenuse. So adjacent to theta is the B right here. And the hypotenuse is C. So cosine of theta is B over C. And tangent is opposite over adjacent. So opposite of theta is A. The adjacent side is B. So tangent is A over B. Those are the main 3 trig functions. The other 3 are reciprocals of the first 3. So the reciprocal of sine is cosecant. So cosecant of theta is C over A. The reciprocal of cosine is secant. So secant of theta is C over B. And the reciprocal of tangent is cotangent. So cotangent of theta is B over A. There are 2 special triangles that you should be really familiar with and have memorized, and that's the 45-45 90-degree triangle and the 30-60 90-degree triangle. Remember, all angles can be expressed in either degrees or radians. So 45 degrees is equivalent to pi over 4. So when I say the sine of pi over 4, that's the same as the sine of 45 degrees. That's equal to root 2 over 2. Cosine of pi over 4 is also root 2 over 2. And tangent of pi over 4 is 1. So these are used often in our course. Then the 30, 60, 90. So let's see, the 30 degrees is pi over 6. And the 60 degrees is pi over 3. So the sine of pi over 3, which is 60 degrees, is root 3 over 2. Cosine of pi over 3 is a half. And the tangent of pi over 3 is root 3. And then the 30-degree angle, sine of pi over 6 is a half. Cosine of pi over 6 is root 3 over 2. And tangent of pi over 6 is 1 over root 3. So you'll see that there are similarities between the 30 and the 60-degree angles. So sine of pi over 3 is the same as cosine of pi over 6, and the cosine of pi over 3 is the same as the sine of pi over 6. And these 2 are just reciprocals of each other when you're looking at 30 degrees versus 60. Okay, so again, really important for you to have those 2 triangles memorized. So here are some common graphs that you should be familiar with, because a lot of the graphs that we will be graphing will be variations of these. So the first one is your linear equation. The most basic of them is y equals x. So it looks like this graph here in blue. It goes through the origin. And the domain and range of y equals x is all real numbers. So that's expressed in interval notation from negative infinity to infinity. The quadratic, or the parabola here, is the most basic one, is y equals x squared. It's got a vertex at the origin at 0, 0. The domain for all quadratic functions will always be all real numbers, but the range will depend on the vertex and the direction that it's pointing in. So in this case, the range is from 0 to infinity, 0 being the smallest value that y takes on, and then it grows from there forever and ever. So y will never be negative in y equals x squared. Then we have our cubic, also a polynomial function. So it's a third degree polynomial. Its domain is also all real numbers, like all polynomials. But here your range goes from negative infinity, because remember this means it's going towards negative infinity, and this goes toward infinity and all values in between. Okay, so let's move on to the square root function. With square root functions, you want to make sure that your domain is only values that will result in a real number result when you take the square root of it. So it could only be from 0 to infinity. There cannot be any negative numbers inside of the square root. And you can see from the graph that your range is also from 0 to infinity. The smallest value that y takes on is right here at the origin, and then it grows from here towards infinity. Okay, then we have our absolute value function. That looks like a v. The domain here, x could be anything, positive, negative, or 0. So it's, again, all real numbers. But you can see from the graph that your range is from 0 to infinity. It's growing towards infinity. It will never be negative. That's what an absolute value does. It changes your negatives to positives. And then we have here two inverse functions, e to the x and ln of x, natural log of x. They are inverse functions, and because they are inverse functions, the composite of two inverse functions, ln of e to the x equals x, and e to the ln of x also equals x. So that will always be true when you take the composite of two inverse functions. The result will be x. So I have e to the x in blue. The domain of e to the x is all real numbers. The range is from 0 to infinity, but this never quite touches the x-axis, so that's why the 0 here is an open interval, not closed, and then it grows very quickly. The natural log has a domain from 0 to infinity. It will never equal 0. It's actually undefined for 0 and negative values. If you tried putting, like, for example, ln of -2 in your calculator, you would get some sort of error message from your calculator. And you can see from the range that this is going towards negative infinity, and then it's growing towards infinity. So your range is from negative infinity to infinity for your natural log. Another attribute of inverse functions is that the domain of one function is the range of the inverse, and the range of one function is the domain of the inverse. So they switch. So basically your x's and your y's switch. All right, so trigonometric graphs. So again, you should be familiar with some basic attributes and be able to graph these relatively easily. So y equals sine of x. With sine and cosine, your domain will always be all real numbers, but your range is going to be between -1 and 1. So it will not take a value on that's greater than 1 or less than -1. It's just going to oscillate forever and ever in this wave fashion. And here I only graphed one period of the function. One period is basically one rotation on the unit circle, so it's 2 pi radians. And at every quarter of the unit circle, pi over 2, pi, 3 pi over 2, or 2 pi, your graph is going to oscillate between -1, 0, and 1. So it starts at 0. At 0, it's 0. At pi over 2, it's 1. At pi, it's back to 0. At 3 pi over 2, it's -1. And then at 2 pi, it ends at 0 again for that first period. So cosine is similar, except it's shifted by pi over 2 units. It still has a domain of all real numbers. Its range is still from -1 to 1. Its period is still 2 pi units. But this time when you're at 0, it starts at 1, and then at pi over 2, the cosine function is 0. At pi, cosine is -1. At 3 pi over 2, cosine is 0. And at 2 pi, we're back to 1. And that again goes on and on forever, oscillating up and down in that same wave fashion. Okay, and then here we have the tangent function. Tangent function is a little bit more complex because it has some restrictions on the domain. Remember, tangent is can also be written as sine of x over cosine of x. So everywhere that cosine is 0, tangent is going to be undefined because you don't want a 0 in the denominator that doesn't have a numerical value. So everywhere that cosine is 0, which is, you can see, it's at pi over 2 and 3 pi over 2, and every pi units to the left and right along the x-axis or theta axis, I'm calling it x in this case, is going to be a restriction on the domain. So the way you state that is that the domain is the set of all x such that x is not equal to pi over 2 plus pi n units, where n is an integer. That's what that fancy looking z represents. Z is an integer, so those would be numbers like -3, -2, -1, 0, 1, 2, 3, 4, etc. So an integer is not going to have a decimal or a mixed number or fraction, anything like that. So your range is the set of all real numbers, because you could see here I have 3 examples of a period of the tangent function. And so you can see that it's going towards negative infinity and growing towards infinity. So your range is all real numbers, and you have an asymptote everywhere that there's a restriction on the domain. So your asymptotes, it's the same numbers. It's x equal to pi over 2 plus pi n, and they are indicated on the graph with these dotted lines. Okay. Logarithms will be important as well in this course. So here's a reminder of the laws of logarithms. Remember, there were 3. We have the power law, the product law, and the quotient law. So the power law says that if you have the log base b of x to the n, that is equivalent to n times log base b of x. So this exponent ends up in front of the logarithm, and they are equivalent. We also have a product law, and the product law said is if you take the log base b of a product of 2 expressions that I'm calling x and y, that the product can be rewritten as the sum of 2 logarithms. So this is equal to the log base b of x plus the log base b of y. And then we have the quotient law, which states that if you're taking the log base b of the quotient of 2 expressions, x divided by y, that is equivalent to the difference of the logarithm. So that is equivalent to the log base b of x minus the log base b of y. All right, so we're going to use those logarithms in order to expand this problem. So I have the log of 3x over the square root of y. So I'm actually going to be able to use all 3 of the laws above. So the first thing I'm going to do is rewrite this radical as y to the 1/2. Remember, I reminded you a few minutes ago how to rewrite radicals as exponentials. You're going to want to do that when you're going to use these log laws. So I have a product in the numerator, 3 times x, so that gets written as the log of 3 plus the log of x. And then I have a quotient, the denominator has y to the 1/2, so it's minus, but I also need to use my power law, which says that I can put the exponent in front of the logarithm there. So that's 1/2 log of y. Notice that I don't have a base indicated. When you don't have a base written in the lower right-hand corner of the log, then that's assumed to be a base 10. So base 10 is not written, it is implied. So when you don't see it, it means base 10 or a common log. Another special type of logarithm is your natural log. So I have the natural log of e to the 3rd divided by x to the 4th y. Remember, a natural log has the same behavior as regular logarithms of any base, but the base with a natural log is base e. So ln of, let's say, x is equivalent to log base e of x. Okay, but this is the common way. This is the way we would typically write it, not like that. Okay, so I'm again going to expand this and simplify as much as I can. So I have a quotient, I have a product in the denominator, and I have some exponents. So first I took care of the quotient. I rewrote this as natural log of e to the third minus natural log of x to the fourth y. And then in the next step, I put the exponent in front of the natural log using the power law. So I have 3 ln of e minus, and then I rewrote this natural log of a product as a sum, which is the second product law. So I have minus, and then in brackets, ln of x to the fourth plus ln of y. And then finally, I did a few things in this last line. I simplified 3 ln of e. ln of e is equal to 1. So that's something important to remember. ln of e is equal to 1. So that leaves me with 3. And then I distributed the minus sign, and I also put this exponent in front according to the log laws. So I get minus 4 ln of x minus ln of y. So that's your pre-calculus review. Thanks for listening.